Okay, let's go ahead and get started. So what I wanted to do today was continue with our discussion of vacuum polarization in quantum electrodynamics. So let me just remind you of where we left off last time. So last time we computed the one-loop correction to the photon propagator in quantum electrodynamics. So in particular, we were considering the time-ordered expectation value of two insertions of the gauge field. So that's the photon propagator, which is a two-index object, usually called capital G mu nu, not to be confused with the metric. And in terms of Feynman diagrams, it's given by the tree-level propagator plus a one-loop correction, where you have a virtual electron-positron pair, plus higher-order corrections that are suppressed by higher powers of the coupling constant, which is the electric charge E. And if you just go ahead and compute this, which is what we did last time, the answer, well, you have the answer for the free propagator, which in Feynman gauge is just G mu nu over P squared. And then the first correction term, well, you get a propagator, I over P squared, times what we called pi mu nu, the vacuum polarization, times another propagator, so another factor of minus I over P squared. Then you would have terms involving 2 factors of pi, 3 factors of pi, and so on and so forth. And I'd use the fact that, technically speaking, I should have a metric here, then a pi mu nu, and a metric. But of course, all of the indices contract together, and you just get a pi mu nu. And so if we want to write that a little bit more succinctly, we can use the fact that the vacuum polarization, or the photon self-energy, pi mu nu, well, at leading order, that's just this one-loop diagram. And last time we argued that by gauge invariance, using the fact that this propagator G mu nu must satisfy the Ward identity, this has to be of the form G mu nu plus P mu P nu over P squared times some function, okay, which we called pi without any indices. And actually, last time I used a slightly different notation where this was a minus sign and this was a plus sign. When I was comparing with the textbook, when I was preparing today's lecture, I noticed that Schwartz uses an opposite convention. So he actually defines everything with a relative minus sign. So that's what I'm going to do from now on. He also defines things with an extra power of E squared there. Okay. So that's just a difference between his definition for pi mu nu and his definition for what he calls pi and my definition for what I called pi last time. So what I'm going to do is just restate our results from yesterday using Schwartz's notation. So here pi, that's something we computed last time. So we've pulled out a factor of E squared, so there's just some numerical constant, which frankly I was a little sloppy about keeping track of yesterday. It's just a matter of tracing it through the calculation. Just some numerical constant. Then we had the integral over the Feynman parameter x, which runs from 0 to 1. And then we had this divergent result. So we computed this in dimensional regularization. So we had a divergence that went like 1 over epsilon, where epsilon is the essentially the parameter that we're using to cut off all of these divergent integrals, which in dimensional regularization is d minus 4. So epsilon is taken to 0 at the end of the day. And so you have this divergent piece, And then you have the important piece, which looks like this. Okay. So if we went ahead and go ahead and plug this back into our expression for the photon propagator will then look like, well, it'll be minus I g mu nu over p squared times 1 minus e squared pi. That's just adding up these two terms here, plus terms that are higher order in e squared, along with terms that involve p mu p nu. And remember that terms that involve p mu p nu in the photon propagator always cancel out in scattering amplitudes because of gauge invariance. Okay. So in this expression, we have dropped the p mu terms, which cancel out anyway in scattering amplitudes by the gauge invariance. Okay. Now, if we wanted to, we could go ahead and keep track of them, but we know that in any computation at the end of the day, the dependence will cancel out. Remember, so here, for example, I'm writing the propagator in Feynman gauge, where it's proportional to the metric g mu nu. But of course, in some other gauge, it would have another term proportional to p mu p nu. And the fact that the theory is gauge invariant at the end of the day means that it's independent of the coefficient of p mu p nu in this computation. That's something that we checked for a variety of different diagrams last class. I didn't actually prove it. It's certainly possible to go through and give a systematic proof using Feynman diagrams, but it's a little tedious and not so important. I mean, it's a true statement. Maybe I'll have you prove it on a problem set, actually. I think that's doable on a problem set. And if not, you'll find out. Okay. Good. Oh, one other comment that I should make is that one can also rewrite this. So here I've just included the term proportional to e squared, the one loop correction. But of course, as with last time, you could also add, you know, the tree level plus the one loop 1 pi piece plus the 2 pi piece, and so on and so forth, where each one of these is a pi. And then when you do that, you'll get, so this would be, so the one loop diagram that I wrote down above would give you something proportional to e squared. The 2 pi piece would give you something proportional to e to the 4th times pi squared. The 3 pi would give you e to the 6th times pi cubed, and so on and so forth. And so in fact, this would sum up into something that looks like I g mu nu over p squared times 1 plus e squared pi. Again, plus other terms that are not important by gauge invariance. So do you remember, so that was the summation that we did last time, where we summed up the 1 pi, 2 pi, 3 pi, and so forth, and saw that they all turned into a denominator form, a contribution in the denominator. And here I've just written that out a little bit more explicitly, using the fact that I can neglect everything that's proportional to p mu p nu in the photon-photon propagator. So today, what I want to do is take this answer for pi that we spent so much time computing last class and spend a little bit of time discussing the physics of this term. Okay. In particular, I want to discuss in a little bit more detail the renormalization of the electric charge and how we define physical versus bare electric charge, and then discuss some of the physical implications of this answer, because this is indeed, I think, one of the real high points of this course. So before I do so, let me pause and see if there are any questions. Okay. So the important point is that this contribution, this quantum mechanical contribution to the photon propagator, leads to quantum corrections to classical electromagnetism. To understand how we can take this answer and interpret it in terms of more familiar objects in classical electromagnetism, let's just consider a simple problem, which is the scattering of two electrons off of one another. So that would be computed by some Feynman diagram that looks like this. So you have two electrons going along, and they interchange some photon. So that would be the tree-level process. But, of course, once we include loops, the photon propagator sitting in the middle here would have to be augmented by the various quantum corrections, including the pi term that we computed last class. So the first thing that I want to do in order to interpret the answer that we derived last class is I want to remind you of something that you hopefully learned in your classes on non-relativistic quantum mechanics. Okay. So in non-relativistic quantum mechanics, in standard quantum mechanics, if we have two particles which interact via some potential that depends on the distance between the two particles, let's call that V of r, then the scattering amplitude is given by a very simple formula known as, well, sometimes referred to as the Born approximation, which says that if you have two particles that scatter off of one another, so this is the equation for scattering off of a potential, then the leading contribution coming from this interaction is just given by the Fourier transform of the potential V of r. Okay. So you need to insert here a momentum-conserving delta function, or an energy-conserving delta function. But, so here Q is equal to P minus P prime. So that's the amount of momentum that is the momentum difference between the two particles. And the coefficient of the energy-conserving delta function is just given by the Fourier transform of the interaction potential. Is this something that you guys have seen before? Okay. This is something that you probably saw. You saw this in some undergraduate quantum class, most likely. Okay. If you haven't seen it, it's actually pretty easy to derive. Okay. So, for example, when you derive Rutherford scattering and stuff like that, in your quantum mechanics classes, this is one of the sort of the central results that we can use. Okay. So what does this mean? So we can now go ahead and compare our expectation from non-relativistic quantum mechanics to the actual result that we get in quantum field theory. So in quantum field theory, if you were to go ahead and compute this set of diagrams here, then at leading order, you would find that you just get E squared over P squared for the scattering amplitude. But then at higher order, you would get these corrections coming from pi. So comparing with the answer that we get in quantum field theory, you see that the potential, the Coulomb potential, or rather the full quantum corrected Coulomb potential in quantum field theory, is then the Fourier transform. Okay, so there's some factors of 2 pi there that just live in the Fourier transform. E to the I q dot r of the 2-point function, of the scattering amplitude. And what is that? Well, that's, you get 2 factors of the electric charge E squared, just coming from these 2 vertices here. And then at leading order, you get 1 over the momentum squared. And then at subleading order, including the 1-loop correction, you just get this correction term, 1 plus pi of q squared times E squared plus higher order terms. So this describes the corrections to Coulomb's law in quantum field theory. So this gives corrections to Coulomb's law. Okay, before we start talking about the corrections to Coulomb's law, just to make you feel a little bit more comfortable, let's just look at the leading term here. Okay. So the leading term, what is the leading term? It's an integral d3q e to the I q dot r e squared over q squared. Okay. The Fourier transform of 1 over q squared, well, we could either compute it or we could just guess what the answer is from dimensional analysis. Okay. So the integral is an integral d3q over q squared, which means that the answer has to scale like q. That is, q has dimensions of mass, which is 1 over length. The answer also has to be rotationally invariant. So that means that it has to scale like 1 over r. Okay. So that means up to some stupid coefficient, which we don't, well, I guess I'll compute for you, but well, maybe up to some stupid coefficient that I'll just tell you. The answer is just E squared over R, which is the usual Coulomb interaction potential. And now we see that we have a correction to the Coulomb potential, which is given in momentum space. Let's just call it V of q by E squared over P squared times 1 plus E squared pi of P squared plus higher order terms. Sorry, I guess I'm mixing P's and Q's. Let's just call it P. Okay. So that's in momentum space. And we could then go to position space by taking the Fourier transform. And indeed, that's what I'm going to do in just a second. Before I do so, I want to make one comment about the normalization of electric charge. Actually, let me pause and see if there are any questions. Yes?
The Coulomb potential, according to Born approximation, is an amplitude, right?
Yes. So there's a relationship
Yeah.
between the Coulomb potential and an amplitude.
Okay, so if we take the quantum field result, leading order, then it should be the amplitude, it should be Lorentz invariant, right? So how is this?
Yeah, I mean, okay, so the answer that I wrote, so this is the answer in non-relativistic quantum mechanics, right here. Okay, P here is supposed to be a 3 momentum. E sub P is the energy associated with that 3 momentum. So square root of m squared plus p squared. So yeah, I mean, at the end of the day, of course, the answer that you get is Lorentz invariant. If you stare at this result that we got for the Born approximation, I mean, it's not obviously Lorentz invariant for any value of v. Okay, But in the case of electromagnetism, V has a very specific form, which at the end of the day, if you work through it, would be Lorentz invariant. I'm not sure if I'm answering your question.
What I want to see is that even the QFT result, even the leading order is at least this one is Lorentz invariant. It corresponds, after that corresponds to the relativistic result.
Yeah, I mean, yeah. Okay, maybe I'm not sure if I understand your question. Maybe I could. Okay, maybe I should be a little. Maybe one comment that I should make is that when we write down this formula, we really think of P as a space-like momentum. So in particular, you should be thinking of P squared being negative. Okay. And P taking the form, as a 4 vector, 0, and then some 3 vector. Maybe I can
Let's
continue, and then we can come back to this if you are unhappy at some point. Good. Any other questions? Okay. Good. Okay, so the first comment that I want to make is that the expression that I gave you for pi up above is, of course, formally divergent. Okay. However, as we saw, the fact that it's divergent doesn't bother us. It's only divergent because we've written the answer here in terms of a parameter E, but I haven't told you what that parameter E is and how it's related to physically observable quantities. So, in order to interpret this properly, we need to define precisely what we mean by the physical renormalized electric charge. So, of course, one way of doing that might be the following. Okay. So one way to do that, which is not actually something that we're going to do, but one way that we could do it is we could take the Fourier transform of the potential V, the full quantum corrected potential that I computed above, and compute it, say, at some fiducial value of the radius, and just demand that it's equal to E squared, the renormalized value of the electric charge, the physical value of the electric charge, divided by 4 pi r naught. Okay. That 4 pi is just the conventional factor that appears in the Coulomb potential. So in this way, we would be in effect defining what we mean by the electric charge to be the force between two electrons at some given value of the radius. Something that's a little bit cleaner and a little bit more elegant would be to actually do this in momentum space rather than position space. Where instead of defining the physical renormalized electric charge in terms of the potential at a particular radius, I'll define it in terms of the Fourier transform potential at a particular momentum. In particular, we'll define E renormalized squared to be P naught squared times V of P naught at some fiducial value of P naught. And in particular, if we wish to define the renormalized electric charge in terms of long distance physics, that is to say very low wavelength physics, then what we will do is set P naught equal to 0. But of course we could use some other value of P naught. Okay. If you have some favorite value of the energy at which it's particularly easy to measure the Coulomb potential, then you might want to use that value to define what you mean by the electric charge as opposed to some other. But the important point is that no matter what value of the momentum you choose, once you write things in terms of the renormalized value of the electric charge, that divergence in pi disappears. That divergence is unobservable. So this is something that we've seen several times before, but I'm going to go through it one more time just because this is kind of the important point. Yes?
This is equivalent to setting the corrected three-point function like electron, photon.
So in fact, this is equivalent to setting the pole of the photon two-point function, or rather the location and the residue of the photon two-point function. Starting at the end of class and next class, we're also going to be considering the three-point function.
Like
The electron-photon.
like minus I, ER.
Exactly. Yeah, exactly. Yeah. That's going to lead us into slightly different sets of corrections involving what are called form factors. Good question. Yeah. So that's something that's the next thing we're going to get to. Okay. So, this set of quantum corrections involving the photon self-energy lead you to quantum corrections to Coulomb's law. Okay, it gives you quantum corrections to the interactions with electromagnetism, quantum corrections to the behavior of the photon. When we talk about quantum corrections to the electron vertex, that gives us corrections to what's basically what you could think of as the structure of the electron. In particular, that's what's going to give us the anomalous magnetic moment of the electron. Okay. That's going to be at the end of class today and next class. Good question. Of course, they're closely related, but slightly different things. Okay, but the important point is let's just go ahead and calculate the relationship between the physical electric charge and the bare electric charge. So let's just plug in this expression for V up here, okay? And let's just work to leading order in the electric charge. Okay? So I'll expand out that denominator, the 1 over 1 plus e squared pi, and I'll write this as, so what is that? That's e squared minus e to the 4th times pi at p naught plus higher order terms. Just working, including only the first non-trivial correction, expanding out this denominator here. And then you could go ahead and invert this to determine the bare electric charge, the parameter appearing in the Lagrangian, in terms of the physical electric charge. Okay. If you stare at it, you'll see that what that has to be is that has to be e renormalized squared plus e renormalized to the 4th times pi of p naught plus dot dot dot. You can check that just by plugging this expression into that one up here and seeing that that's just going to give you ER squared is equal to ER squared plus corrections that are of order e to the 6th. So in particular, because pi has a divergence, this means that e squared has a divergence. The bare coupling has a divergence. But this divergence is unobservable. In particular, let's say you want to calculate v at some other value of the radius or some other value of momentum. So that's 1 over p squared times e squared minus e to the 4th pi of p squared plus dot dot dot. And then you can just plug in our expression for E in terms of the renormalized charge. And you get 1 over p squared times E renormalized squared minus E renormalized to the 4th. And And then we just have to include this correction term here in that expression for E squared. And we get a pi of P minus pi of P naught squared. Plus dot dot dot. And then if we go ahead and stare at our expression for pi up here, okay, so here was our expression for pi, you can see that when you subtract off pi of p minus pi of p naught, that 1 over 2 epsilon divergence just cancels out. So in particular, we get a term, an expression which is completely finite for the correction term to Coulomb's law. So you get the usual E squared over P squared, and then you get a 1, and then you get plus E squared term. There was that 2 pi squared. I think there's a minus sign somewhere. Is there a minus sign, hopefully? Yeah, so there's this minus sign here. Okay, that sign is important. That's actually an incredibly important sign, which gives you that plus sign here. And then you get this integral. And then you get the logarithm that appeared in the expression for pi. So I wrote that logarithm as the log of m squared minus p squared. So I'm going to rewrite that as the log of 1 minus p squared over m squared times x times 1 minus x. I can do that because I'm subtracting off an overall constant term in pi, so I can just set it to be whatever I like. And I've set it here so that it looks like the log of 1 plus a constant, or 1 plus something. And the important point is that this is perfectly finite, and that this describes the corrections to Coulomb's law. Oh, one comment that I should make is that in this final expression here, I've defined my value of E renormalized so that it's equal to p squared times the Coulomb potential as p goes to 0. Indeed, you can check that when p goes to 0, you just this term is 0, so you get the log of 1, which is 0. So this quantum correction just completely vanishes as p goes to 0. And v, as p goes to 0, goes like E squared over p squared. So here, your E renormalized squared is defined to be the limit as p naught goes to 0 of p naught squared v of p naught. So this is defining the physical charge in terms of a long distance physics. Later on, actually, it'll be convenient to define it slightly differently, but this is what I want to do for now. Any questions on this? Yes.
I think the question was in the last class as well. Basically, we are treating p and pi as a small variable when we involve the denominator.
Indeed.
But it actually diverges, so there's kind of some.
Okay, but you see that the actual physically relevant quantity is not the divergent one.
Yeah. But
The at the end of the day, okay, at the end of the day, so pi is divergent only if you insist about talking about physically unobservable quantities. If you insist on talking about physically observable quantities, then everything is perfectly nice and convergent. So for example, if E is a very small number, if the electric charge is small, then this correction term here is small compared to 1.
So basically, we have two parameters: the electric charge and the regularization parameter, depending on which one is.
No,
sort of
the regularization parameter is completely dropped out of this expression.
But that's after we already endorsed
Okay. I mean, this is sort of an important point. At intermediate stages in the calculation, pi can look divergent. But that's only because you've written things in terms of unphysical quantities. You know, you wrote things in terms of e squared pi squared. E was, let's put it this way. If you are a little sloppy, and indeed we're being a little sloppy here, and this is usually how people work in quantum field theory, is by being a little bit sloppy. If you work in terms of the bare parameters that appear in the Lagrangian, then things can appear divergent. But that's only because you're working in terms of physically unobservable quantities. If you work in terms of observable quantities, then as we've seen, everything is nice and finite and can be small if the coupling constant is small. The answer that we got here at the end of the day is completely independent of any regularization scheme. It's completely independent of the cutoff scale. There's no epsilons appearing anywhere. Okay. I mean, that's an incredibly important point. Otherwise, quantum field theory would be useless, right? If this depended on the cutoff, then that would mean that you couldn't, you couldn't talk about the weather without knowing QCD, right? It would mean that you couldn't talk about low energy physics without understanding high energy physics. It would mean that you couldn't have a theory of atoms without knowing the theory of nucleons. And you couldn't have a theory of nucleons without having a theory of quarks. You couldn't have a theory of quarks without having a theory of quantum gravity. So, the fact that you can use a quantum field theory to make a prediction in terms of low energy physics without referring to high energy physics is kind of the reason why quantum field theory is useful. That's like, if there's one important point this semester, that's kind of the point. Yes?
So, I guess I have a question about that statement.
Okay.
If that makes sense to me. We've managed to get our cutoff parameter, to remove our cutoff parameter from our expressions for any kind of physical quantity.
Yes.
So we say that, okay, we can now let it be arbitrarily large and it doesn't matter anymore.
Yeah.
Because it doesn't appear in our result.
Yes.
Okay.
But it also doesn't have to be arbitrarily large.
Yeah, so that's my question. Okay, so
Right,
I
good.
get to say that, okay, everyday physics doesn't depend on, we don't have to know about quarks to be able to figure out how this pen falls,
That's
or
right.
anything like that.
That's right.
But
However,
I could just as well say,
if you want to put a pen in a particle collider and collide them together at relativistic energies, then you do need to know about quarks, right? So, yes, maybe,
Okay.
but maybe that wasn't your question.
my question was that we could also just as well say, this expression is independent of lambda. Let's let lambda be as small as we want. Now we don't know. Now apparently we don't have to know anything other than we don't have to know about anything other than far infrared, radio waves.
Well, it depends. In all of the calculations, I assumed that the cutoff scale was larger than the momentum at which I'm studying here.
You're expanding small.
Yes, exactly. Yeah, I mean,
Oh yeah. Okay, yeah.
yeah. I mean,
That makes sense.
yeah.
Like the intermediate stages of this calculation, it's just an arbitrary
Yeah, I mean,
That's
right.
That's
Okay, that's a
okay.
good way of
Thank
saying
you.
it.
That's what I
Yeah,
was looking for.
yeah. Now, okay, good. Thank you. Other questions? So let's just go ahead. Yeah, I mean, it's a very important point that this result is cutoff independent. And moreover, that it depends on only two parameters. It depends on the physical electric charge, and it depends on the momentum at which I'm studying Coulomb's law. Okay. So the first thing that I'd like to do, just to make contact with some physics that you already know, is I'd like to study this at long distances. That is to say, at very low momenta. Oops. So at very low momenta, we can go ahead and expand this logarithm. Okay. So the integral that we're left with is the integral dx, x times 1 minus x, log of 1 minus p squared over m squared, x times 1 minus x. So what is that? So the leading term at p goes to 0 is just, the log of 1. Okay, that's 0. So that doesn't affect us. The first leading term is goes like p squared over m squared. There's a minus sign out front. That's this minus sign. And then you just get the integral dx of x squared times 1 minus x squared, which is a constant that is easy to compute. It's 1 over 30. So that means that at very low values of p, at very long distances, the potential, well, you have the E squared over p squared piece. That's just the usual Coulomb's law. And then you get a correction to it. The first correction is minus e to the fourth over 60 times pi squared m squared. So you get a constant term plus higher order corrections in p. Or, if you take the Fourier transform, well, I told you that first term Fourier transforms to the usual Coulomb law, so 1 over r. And the Fourier transform of a constant, which is the second term, is just a delta function. So you get minus e to the fourth for 60 pi squared m squared times a delta function. Okay. So this is the first correction to Newton's law due to the virtual electron-positron pairs. And in fact, this leads to observable effects. In particular, this shifts the energy levels of the hydrogen atom. So first of all, that correction term is very small. So we can treat it as a perturbation to the Hamiltonian of the hydrogen atom and treat it using standard perturbation theory in non-relativistic quantum mechanics. And if you add a small perturbation to a potential in quantum mechanics, then that shifts the energies of the states in the theory. And at leading order, the shift in the energy of a state is given just by integrating the norm of the wave function of that state times the change in the potential. Okay. That's just standard time-independent perturbation theory. So in Braun-Ket notation, that just says that the change in the energy level at leading order is the expectation value of the change in the Hamiltonian. And now delta V is just a delta function. So that's just e to the fourth over m squared times the value of the wave function at the origin. Okay. So the change in the energy level at leading order depends only on the value of the wave function at the origin. So now I want to remind you what the wave functions of the hydrogen atom look like. The wave functions of the hydrogen atom are characterized by their angular momentum. The S-wave wave functions are those which have no angular momentum. P-wave have 1 unit of angular momentum, and so forth. And the only wave functions which have support at the origin are the S-wave wave functions, the ones with no angular momentum. So this shifts the energy levels of the S wave, that is to say, the rotationally invariant states of the hydrogen atom, but not any others. Because those are the only states where the wave function is non-zero at the origin. For all the other states that have angular momentum, there's an infinite angular momentum barrier that keeps the wave function away from the origin. It sets it to 0 at the origin. So in particular, in the hydrogen atom, as you may or may not remember, but it's a true statement, in the hydrogen atom, two of the simplest excited states, namely the first S wave and the second S wave and the first P wave states, are degenerate in standard non-relativistic quantum mechanics. But this gives you a correction that affects the S wave state but not the P wave state, that if you go ahead and plug in the numbers, is small but observable. So this is a contribution to what's known as the Lamb shift. And it was, in fact, one of the very first pieces of experimental evidence for quantum field theory. So the computation of the Lamb shift using quantum electrodynamics was, I believe, first done by Feynman, Schwinger, and Tominaga. I think they all won the Nobel Prize for it, but I think only Tominaga actually got it right the first time, if I remember correctly. But in any case, this is indeed, I think, one of the most important results in quantum electrodynamics. And more generally, we can keep more terms in V of r at large radius to get higher and higher corrections to the Coulomb potential. And just for fun, let me just write down for you, I'm not going to do the calculation. I think it's not that hard, actually. It's just a Fourier transform. I'm not going to bother to do it. I think, well, I guess I could have given it as a problem on my problem set, but, you know, there's more to life than Fourier transforms. Maybe, not sure. Probably. But the first correction looks like this. Okay. So you can see here all of the corrections are expressed in terms of the dimensionless combination R times M, where M can be thought of as 1 over the Compton wavelength of the electron. That's the length scale on which the quantum effects to the electron would be relevant. And then for R much bigger than the Compton wavelength of the electron, this is the leading term in the quantum correction to the Coulomb potential. And this correction is known as the Euling potential. Okay, I believe that's how it's pronounced. Maybe he was Swedish. One could go ahead and compute systematically using, for example, time-independent perturbation theory, how these various subleading corrections would affect the energy levels of the hydrogen atom. So this is the correction to Coulomb's law due to QED effects at very long distances. What I think is even more interesting is, and what's going to be more important for the rest of this course, is the consideration of what the corrections to Coulomb's law look like at short distances. So that's what I'm going to consider next, but maybe before I do so, I can pause and see if there are questions. Any questions on this? Did you guys study the Lamb shift in quantum class? You did. Okay. You obviously didn't do this term in the Lamb shift, but there are other terms that I know that you can compute much more easily by just looking at the relativistic corrections to the Hamiltonian. What did you do when you compute? Okay, it's okay. You can tell me some other time. But I'm curious what you actually did when you computed the Lamb shift. Good. Okay. So let's study this potential at large P. Okay. So at very short distances, so again, so this is the formula that we're looking at here for V of P. So we need to expand out this guy at large P. So we have a log of, what was it, 1 minus p squared over m squared, x times 1 minus x. So at large P, that just looks like log of minus p squared over m squared plus times x times 1 minus x, which I could also write as plus log of x times 1 minus x, then plus various terms that vanish as we take p to infinity. So that means that the Coulomb potential then has an e squared over p squared 1 plus log of minus p squared over m squared, and the coefficient of that log was e squared over 2 pi squared, and then we just had the integral dx of x times 1 minus x, which is 1/6. And then the first correction to that is just given by, well, the integral dx of x times 1 minus x times log of x times 1 minus x, which is some constant. I think it's 5/3 or something like that. But it's not particularly important. But you get a whole series of corrections that are suppressed as p goes to infinity. One important point to keep in mind here is that the momentum p is spacelike, so minus p squared is positive. And we're taking minus p squared to infinity. So that the argument of the logarithm here is large and positive. So what this means, if you think of the Coulomb potential at a given value of the momentum p as defining for you what you mean by some sort of effective charge, it means that the effective charge as a function of the momentum squared, okay, so we could just define that to be p squared times v of p squared. So that's e squared times 1 plus e squared over 12 pi squared times the log of minus p squared over m squared plus dot dot dot. Where this e here, I should make clear, is the renormalized energy. Or, sorry, the renormalized electric charge. There's one small subtlety with this formula that I should point out. Strictly speaking, I defined E renormalized to be the value defined in terms of the potential at P is equal to 0. But if you look at this expression here, that guy has a divergence as you take P to 0. That's because I'm examining the formula in a large P limit, and so I've thrown out the terms that make this finite as you take P to 0. So if you stared at this formula and said, how is E renormalized defined? It looks like E renormalized is defined at P squared equals to M squared. Okay? Because if P squared equals to M squared, this becomes the log of 1, which is equal to 0, and you would have E effective of M squared is equal to E renormalized squared. Okay? That's because we're working, I'm writing down this formula at very large momentum, and so you can't actually really tell the difference between P squared equals 0 and P squared equals M squared. But there's something very important that we should conclude from this formula. And it comes from this sign here. It comes from this positive sign right here. In particular, we see that the effective value of the electric charge increases as p squared goes to infinity. So at very short distances, the effective value of the charge increases. So how should we interpret that physically? Physically, the way that we interpret this is that it reflects the fact that in quantum field theory, empty space is not as simple as it is in classical mechanics, or even in non-relativistic quantum mechanics. In particular, it's a dielectric medium. Okay, what do I mean by that? Well, a dielectric medium is one that contains charges, and in particular, it has the property that if you place a charge here, so let's imagine placing a charge right here with some value of the electric charge, then if you're standing very far away, that charge is going to be screened by tiny dipoles. Okay. So in particular, well, I guess it should really be minus plus. If the electric charge, so if an electron has negative charge, then you would attract the positively charged end of a dipole and repel the negatively charged one. So really, when you are, if you're standing here very far away from the electric charge, then the electric charge you see is actually screened by all of these dipoles. And so the apparent charge at long distance is going to be much less than the actual charge. So you could really think of the bare electric charge as sitting there at the origin, and the physical electric charge is only what you measure, and that's after you take into account the screening coming from all of the little electron-positron pairs that pop out of the vacuum because of quantum effects. And indeed, this is something that happens not just in quantum electrodynamics, but also in much more conventional systems, condensed matter systems, any sort of a metal, for example, any sort of system where you have free charge-carrying excitations. You'll get screening of electric charge, and it would be described in precisely the same way as we're describing it here. Okay. So let me just go ahead and make one more comment about this formula. So the effective charge, so what was that? That was the renormalized charge times 1 plus the renormalized charge over 12 pi squared times log of minus p squared over m squared plus higher order corrections. That 1 here is the leading tree level term, and this term here is the one loop term. And all of these subleading terms come from 2 loop and higher terms. But if you stare at this formula, what you see is that as p goes to infinity, the one loop term will eventually become larger than the tree level term. That means that your perturbation series is breaking down. The only reason why we trusted this Feynman diagram expansion in the first place is that we assumed that the electric parameter E was very small. But what we see here is that at sufficiently large values of P, the one loop term is going to be bigger than the tree level term. And in fact, the 2-loop term will then be bigger than the 1-loop term, the 3-loop term bigger than the 2-loop term, and so on and so forth. And so that means that perturbation theory is breaking down. If you want to do this a little bit more carefully, you should take into account the fact that the perturbative parameter in the Feynman diagram expansion is not actually E, but it's actually the fine structure constant. So alpha is E squared over 4 pi. It's about a 1 over 137 at low energy. But here you see that the effective coupling constant is given by 1 over 137 times some corrections. So you get 1 plus, so from this term here, 1/4 1 over 137 times the log of minus p squared over m squared plus dot dot dot. So that means that the perturbation series is breaking down when this effective coupling constant is of order 1. And you see that because of this logarithm here, p is actually going to have to be exponentially large in the electron mass m in order for alpha effective to be of order 1. If you put in the numbers, I think it's about 10 to the 286 electron volts. Okay. That's very, very high energy. Much higher energy than anything that's going to actually be relevant for any sort of particle physics. And in fact, we can actually take this one step further. Okay. Because actually, if we did this a little more carefully, remember that we had an expression for E effective squared in terms of E squared plus E to the 4th plus so on and so forth. Well, those so on and so forth terms are terms that we could actually control. Right? Because they were all of the various terms. They were the 2pi, 3pi, 4pi terms, and so forth. So actually, if you study this a little more carefully, you get E squared over 1 minus ER squared over 12 pi squared log of minus p squared over m squared plus dot dot dot. And that comes from summing up the 1-loop contribution to the 1pi effective action, to the 1pi self-energy pi, and then having the pi plus pi squared plus pi cubed, summing up into 1 over 1 minus pi. So you actually see that when this term here becomes equal to 1, you don't just have alpha effective going to 1. You have alpha effective going to infinity. As p goes to this critical value, which is about 10 to the 286 electron volts. So if we were to make a graph of the coupling constant as a function of energy, so if this is the effective coupling constant, so let's actually graph it just for fun as a function of radius. Then at very long distances, the coupling constant is approximately a constant. It's 1 over 137. But then, as you probe the theory at shorter and shorter distances, the coupling gets stronger and stronger and stronger until at some finite value of the energy, some finite value of R, the effective coupling constant diverges. So this phenomenon is known as a Landau pole. And it means that not only is perturbation theory breaking down, but because the effective coupling constant is going to infinity, really quantum electrodynamics is not even really a well-defined theory. At arbitrarily short distances. So it just, on its own, quantum electrodynamics does not make sense as a quantum field theory. Because if you consider the quantum corrections to the coupling constant, you find that you have this divergence at some large but finite value of the energy. So this is going to be in contrast to some other theories that we'll study later on in this course, which have the property that that crucial sign that I computed was a minus sign rather than a plus sign. So they get more weakly coupled as you go to high energy rather than more strongly coupled as you go to high energy. Let me pause here and see if there are any questions. I bet there are one or two. Yes?
This energy response to very, very small pieces, much smaller than the Planck scale.
Much smaller than the Planck scale. The Planck scale is 10 to the 17 eV or something like that. So this is not something that's actually relevant for our physics. You know, quantum electrodynamics is already wrong at the weak scale, okay? You know, at the MeV scale. You know, 1 million electron volts. So, you know, you already have to correct it to account for nuclear interactions and stuff like that. So, this is not relevant for actual physics of our world, but it's a very important point about quantum field theory. You can sort of divide quantum field theories into two different classes. Okay? There are the classes where the coupling where a coupling constant becomes strong at short distances, and then there are the classes where the coupling constant becomes weak at short distances. Those quantum field theories where the coupling constant becomes strong at short distances are not well defined on their own. And quantum electrodynamics is one such theory. The reason why quantum chromodynamics is a good theory of the strong nuclear interactions is that it has the opposite property, that it becomes weakly coupled at high energies. It's strongly coupled, actually, at low energies for nuclear physics, but for high energy physics of the sort you would do at an accelerator, it's weakly coupled. That's why that's really why the standard model of particle physics kind of makes sense on its own as a complete predictive quantum field theory. Yes?
I've seen dielectrics before that are much better than vacuum. These ones. Makes me wonder if there are any condensed matter systems that have sort of big Landau poles.
Landau was a
accessible-
condensed matter theorist, so that should give you a hint.
Yeah. So yeah.
Yes. So yes. This is, what this means is that when you have a Landau pole, there must be some new physics that takes over. And so, this is one of the great things about quantum field theories is that quantum field theories often predict their own demise. Okay. Quantum electrodynamics is predicting its own demise. If you just had a theory of quantum electrodynamics and nothing else, then you would know that there would have to be some new physics at the scale. Now, in fact, it turns out there's new physics 280 orders of magnitude below this scale, okay? But just on its own, just for purely self-consistent reasons, you know that there would have to be new physics at this scale. And this does happen in condensed matter systems. Good question. Yes?
Well, you said way back when you picked the value for the coupling constant
Yes.
at a certain, well, you said
Yeah.
you do it at a certain length scale.
Right. Good.
Yeah, in light of this, could we not have done it?
You could not have done it. Right. You could certainly have picked the coupling constant to be at that scale instead of at that scale, and you would have no problem. But if you tried to pick it at this scale over here, you would have been in trouble. Because you would find that, in fact, your expression for the Coulomb potential just diverged. Yes. Excellent questions. Okay. indeed, the study of the behavior of the coupling constants with energy. So this, pictures like this are very important. So the fact that the effective coupling constant changes with energy is sometimes known as the running of the coupling constant. With energy. And this is something that we're going to study systematically and in a lot of detail in the next several weeks. This is the first example of that. Any questions? Other questions? Okay. So this completes the discussion of the photon self-energy. There's one other important classic result in quantum electrodynamics, which is the anomalous magnetic moment of the electron. That's what I wanted to do now. I've only got 9 minutes left, and I went over last time, so I don't think I'll be able to do anything terribly useful with it in the rest of class. So maybe we'll just end a few minutes early, or maybe this is a good time for any other questions, if people have other questions. Yes? No. No, I don't think so. I think that, okay, I don't want to say anything. That might be incorrect, but the answer is no. Yes.
There was some observation that the fine structure quantum is not quantum over
Yeah.
space or space.
That's, over space or space-time.
Well,
I mean,
there's some contradiction.
there's some controversy over it. Well, let's put it this way. So this running of the coupling constant is logarithmically slow, right? If you look at this correction here, it's got a log, which means that you have to double the energy to get a constant change in the effective coupling. So this running of the electromagnetic coupling, the Franz structure constant, is observed, but it's kind of difficult to observe. I mean, I don't think it's, it's not one of these, this high energy the fact that this term changes with energy is, I think, difficult to observe, and I think it's probably only in the last couple decades that it's been observed. But there are also people who claim the fine structure constant changes in time or space. That's more of a cosmology discussion.
So it has nothing to do with the triangles.
Yeah,
Even
as far as I know, it has nothing to do with it. Yeah. Okay, maybe I'll stop here and see you on Tuesday.